Solvent systems and phase diagrams. My goodness. Let's start simple. To do countercurrent chromatography, we need at least 2 solvents. Since we need 2 phases, 2 immiscible phases, we need at least 2 solvents. Every time it's possible to work with 2 solvents, just go for 2 solvents. That's the simplest way. So when we have 2 solvents, it's easy to prepare. Just mix the 2 solvents and wait for thermal and chemical equilibrium. So for example, octanol and water are 2 solvents that are very often used in CCC to measure octanol water partition coefficient, injecting the compound and getting retention time, which is related to the octanol water partition coefficient, which is a parameter required by the FDA, for example, or for the pharmaceutical company to get a new drug accepted. So if we take octanol and water, we should know that octanol contains 4% of water, which is 35 grams per liter, or close to 2 molar. It's a lot. And the lower phase, the aqueous phase, contains only 0.05 in weight of octanol, which is only 540 ppm or 4 millimolar. So that's very important. You mix octanol and water. A significant amount of water goes in octanol, and almost no octanol goes in water. So what does that mean for us in CCC? It means when I am running octanol water partition coefficient, I put octanol as the stationary phase, and I am running with water. So I know that in water I have just 540 ppm of octanol, a very low amount, and I need a lot of water because that's my mobile phase. So I can just prepare octanol water, equilibrate very well the stationary phase, say overnight, load the machine, and then I need liters of water, but I can just take distilled water, put a little octanol, shake, not waiting and using immediately. Because I know if there is ppm octanol missing, it's not critical. So that's not my point I wanted to do today, but since we are talking about this, I have a student doing octanol water at the moment in my lab, and it's terrible. The smell is terrible. I have everybody else in the lab coming. It stinks, it stinks. And I am keeping, it's not toxic, you know. But they're right, it is not recommended because it's hiding other smell, and that's toxic. Okay. Octanol water, it's just octanol and water, and it's very easy to work with this, and it's very useful in CCC. And by the way, this is the most important analytical use of CCC that I know. That's analytical chemistry, that's not prep. Okay, octanol water. Another one is butanol water. Just put butanol and water, and with butanol you have even more water going in the butanol phase, but you have a significant amount of butanol going in the water phase. So you must prepare your butanol water system, let's say a day before, let it well equilibrate, shaking from time to time. You have 20% in weight, or 200 grams per liter, 11 molar of water going in the butanol phase, and you have 8% of butanol, which is 1 molar, it's significant, going in the lower phase, the lower aqueous phase. So that's the only thing I want you to know when you work with 2 solvents only. Just don't show up mixing the 2 and work. Very often you need time to equilibrate. That's very important to have them well equilibrated. If you don't, it will work, but it will not be reproducible. And you will ask, why is different today, was not the same yesterday? just because it was equilibrated today and not yesterday, or vice versa. Methanol heptane is a mixture that has 31% of heptane in the methanol phase. Yesterday we tried this one, and I forgot your name. You tell me, I guarantee I put the same amount. Yes, you did. But when you look at the tube, you have a thin layer of heptane and a big layer of lower phase. Because of this, you have 31%, one-third of your heptane goes in the methanol phase, and of course the methanol phase inflates and become bigger in volume, and the heptane phase decreases one-third. So you say, I made a mistake. And this system is one which equilibrates very fast. It's very quick. The two solvents are well compatible. It's equilibrated very, very fast. In 2 minutes, it's equilibrated. The upper phase doesn't have any very small amount of methanol. 1,000 ppm of methanol goes in the heptane, and 31%, this is for 20 degrees, and the temperature is very important. I think that the critical temperature of heptane and methanol is 45 degrees. You take the mixture in your hand, you may get one phase. So this system, pure methanol and heptane, is not very much recommended in CCC because you have heating in CCC, and that may be very difficult to work with this. Okay, binary system, the simplest system. We don't need phase diagram. You just need to open the table and look solubility of one phase in the other, and you can work after equilibration. When it becomes more difficult, it's when you use free solvent system. So if you use free solvent system, and we want to have a picture of the mixture, a picture on the paper is only two-dimensional. So we need to reduce the free A and B and C proportion to 2 proportions so we can put them in 2D. So that's not difficult. Instead of putting the amount in volume, we will consider the full volume and work in percentage, writing that percentage of E plus percentage of B plus percentage of C, it's 100%. So if you say this, then you have just 2 parameters. Percentage of A is whatever you want, percentage of B is whatever you want, and percentage of C is 100 minus percentage of E and percentage of B. So that you have this relationship, sum of the 3 is 100%. So then we can make ternary phase diagram in 2 dimensions with just percentage of E and percentage of B, percentage of C being calculated. When we prepare phase diagram, we must say its phase diagram in volume, because the percentage of volume is one way to calculate. It can be in mass. I think tomorrow we will do in mass, but it's your choice. If you do in mass, you need a balance. If you do in volume, you need a pipette and a burette and that kind of things. But of course, you can calculate one using the other one because we know density, we know molar mass of all those compounds. So it can be in mass, it can be in volume, or it can be molar, in mole fraction. You choose. But it's important when you look at phase diagram that's published, is it mass, is it volume, is it molar fraction? Because it changes a little bit. So this is the representation of a ternary phase diagram on the left. So that's the usual presentation. It looks like an equilateral phase diagram with 60 degrees 3 times. You put solvent A, your choice, on the left. If you have water in the mixture, usually water is there, but I never found any rule saying it must be there. It's usually there because it's convenient. When everybody put it on the lower left corner, then when you read the phase diagram, it's convenient, but it's not required. So solvent number 1 is solvent number 2 and solvent number 3. There is one rule. If you have a phase diagram, it means you have some solvents that are not completely miscible. If you have 3 completely miscible solvents, it's not really necessary to make a phase diagram. Whatever proportion you put, you will get 1 phase, and your phase diagram will be a triangle with nothing in it. So usually you must have at least 2 solvents that are not miscible. And those 2 solvents that are not miscible must be at the bottom, at the basis of the triangle. So for example, in that example, solvent 1 and solvent 3 are not miscible or are very partially miscible here and there. You don't see it. And then I have solvent 2, which is fully miscible with solvent 1, and solvent 2 is also fully miscible with solvent 3. So what happened when you mixed solvent 1, solvent 2, and solvent 3, there are proportions with 1 phase is in white. This will be 1 phase region. You cannot work in CCC with 1 phase, you need 2 phases. And there are mixture of the 3 where I have 2 phases. That's what I am interested in to do CCC. That's in blue on that slide. Okay? So blue part, biphasic region, white part on that slide, but in publication you can have H area or tell you where it's 1 phase and where it's 2 phases. This line, the borderline of the biphasic region, is called binodal curve. That's the limit. So we need to find that's binodal curve. That's what we will do this tomorrow afternoon. This afternoon, no, tomorrow afternoon. Binodal curves, okay? In these binodal curves, you have 2 phases. And this phase diagram tells you what the proportion of the 2 phases are by the tie lines, those lines. The tie is this thing, it's called a tie. It's binding 2 proportions. So those lines are the tie lines. How do you use this? If you have a proportion, it tells you any proportion of that line goes there and there as a proportion. I'll go on this point in detail in a minute. On the left, that's the normal and I would say PChem, physical chemistry representation of ternary phase diagram. It must be 60 degrees of angle here, 60 degrees of angle there, 60 degrees of angle there. That's the normal way. Then you can put a ruler and make measurement. It's all valid. This is very difficult to use in modern software, Excel, or I don't make any commercial, but you know, Quattro, or because it doesn't make this drawing very easily. It makes this one very easily. So that's the orthogonal representation. What does this mean? In this one, all the X, the Y and Z, or A, B, and C, you know, the percentage of the free solvent, are in columns. And I just need 2 columns, actually. A, B, C, it's 1 minus A and minus B. And then when I have A and B, it's easy to tell Excel, draw me the picture, and you get this picture with right angle here, because this is A or Y, and this is B or X. Let's make you an X, Y, and everything you see is distorted a little bit. But so you cannot put directly a ruler on this to get distances. But you can read very well the composition. This composition is correct, this composition is correct in X, Y, and you find Z also. So this would not be accepted for publication in a physical chemistry journal, but it's very convenient to work this way. And that's equivalent. Okay. So now let's comment what we can observe. So every time I put on the left the equilateral triangle and on the right the orthogonal triangle. Same, that's the same, and that's the same. I just use an example of mixing three solvents, which is the most common solvent. You have two immiscible solvents, and you want to adjust the composition of the two phases, making a third solvent, solvent 2 in that case, which is miscible in the two other, and will partition the solvent 2 itself, will partition between those two, solvent 1 and solvent 3, making changing properties in your system. So that's one case, and that's the most common case. We use this case a lot. But there is other case, for example, this case, which is just what Vilda talked about. That's the case butanol acetonitrile, butanol ethyl acetate water, for example, or octanol hexane water. Solvent 1 and solvent 2 are completely miscible, but solvent 2 and solvent 3 are not completely miscible, and solvent 3 and solvent 1 are not completely miscible. For example, butanol and ethyl acetate are completely miscible. By the way, butanol would be on the left on that case. So I should present it. If it's butanol ethyl acetate water, I should present it this way. Doesn't matter, right? Butanol and ethyl acetate are completely miscible, but butanol is not miscible with water completely, and ethyl acetate is not miscible with water completely, just a little bit on each side. So you get this design. You have a biphasic area between two monophasic areas. Not just one monophasic area like we have in type 1. So you have two binodal lines, one here and one there, and the tie lines are this way, for example, same representation orthogonal. And there is a third type of ternary system, which is called type 0, and to my knowledge there is just one, but maybe with exotic solvent there is more. This solvent is useful in CCC. It's tetrahydrofuran, dimethyl sulfoxide, and water. If you take THF and water, completely miscible. If you take DMSO and THF, completely miscible. If you take water and DMSO, completely miscible. 2 by 2. You put the 3, you have a good chance to get two phases. This is interesting. Those two phases have different proportion of the 3 solvents, but you have two phases, and it's possible to work in CCC with THF, DMSO, water. That's make a very polar solvent system, but interesting. So let's go to the way you work with those phase diagrams. You have your 3 solvents. So in that case, I took as an example chloroform, methanol, and water. 3 solvents: chloroform, methanol, water. I decide to draw my phase diagram this way. I put water lower left. Why? Because it says so in the curse. Okay. Then I put chloroform there because I must do this way, because chloroform is not soluble with water. Okay? Then I have methanol at the top, because methanol, that's the common solvent. It's soluble with chloroform and soluble with water. You realize that you must have some knowledge, some chemical knowledge, when you want to work with phase diagram. How do you know that methanol and chloroform are soluble? Either you take a book that's called Merck Index, or a handbook of chemistry and physics, of whatever, and you look in the book, or you can type Wikipedia on keyboard if you want. It works also. And that's tell you methanol and chloroform are soluble. Okay. Or you remember from course and you know it. So this means this point will be methanol, this point will be water, and these points are called apexes. It will be chloroform. Then I have to make graduation of my side of the triangle. So, for example, this side going from water to methanol. On the slide, I put water percentage. It's not required. I could put methanol percentage. Okay? But if I put methanol percentage, 20% should not be there. 20% should be there. So, okay, you choose what you want. For example, it can be, of course, water or methanol. It cannot be chloroform. There is no chloroform on that line. It's water, methanol. So it must be water or methanol. I choose water. But once you have choose water, look at the angle of these sticks. It should be, since it's water, the tick should be parallel to the water apex, this way. If I choose methanol, I can, but this will be 20 and not with a tick. This way, methanol between here should be this way, methanol. So this angle is important. It's 80% water here, not there. That's methanol. That's water. Okay, water, water. Methanol, methanol. So I choose water, the tick must be this way. Okay? I would say 99 articles over 100, they don't do that because it's difficult to print. And even Excel, and it's always horizontal or vertical here. So that's you must remember, if it's water, I read it, water is here, I should not touch it, I should be this way parallel to the opposite basis to the water apex. Then, when I choose water here, I have to graduate that one also. On that one, I have choice between chloroform and methanol. But I have no more choice because I put water here instead of methanol. If I put chloroform here, then I cannot put anything down here. Because here it must be water, I already put it there, or chloroform, I already put it there. So I cannot put chloroform here, must be methanol. So if it's methanol, methanol is there, should be parallel to this line, opposite to methanol apex. This is the tick, horizontal ticks. Okay? And the last one, on that line you have choice between chloroform and water, but chloroform is already, no, chloroform is free, so this is chloroform. It doesn't show. Okay, you may have it printed. No, it disappeared. But that's chloroform tick, going from 20 to pure chloroform 100 here. Okay, question on this? So this is very important to have a good label on your drawing. And next, it's just reading. So as an example, I theoretically prepare this composition, chloroform 37.8%, methanol 44.8%, water 17%. Where is it in the diagram? So you start with the first one, chloroform 37.8. I have my ticks ready. I look where 37.8 is. This is 20, this is 40. I have a ruler, this is 37.8. So my point is on that line. Where on that line? I look the second proportion, methanol. Methanol is 44.8%. Where's my methanol graduation? Here, where is 44.8? 40, 50, 44.8, it's here. And that's it. I have my point. Oh, you have your point with 2 only? Yes. because the last one must be the complement to 100. Last one is 17.4. You can check it if it's correct or not. But 0 is there, 20 is there, 17.4 here, and of course give you the same point. So you just need 2. And the third one is to confirm if needed. Okay. So I choose this composition because in the methanol, real methanol water chloroform diagram, that's the plate point. I'll explain what the plate point is in a minute. So now let's look at the full chloroform water methanol phase diagram, which is this one. It's published, it was published. Walter didn't prepare, you didn't prepare that one, you found it somewhere. I thought the first time I saw it, it's in your book.
Yeah, it's in my book.
So this is the full diagram. In blue, 2 phases. In white, 1 phase. We will see tomorrow or Walter got it or got student making it. So let's look at it. We have the binodal curves that make the boundary between 2 phases and 1 phases. In CCC, you can just work with blue composition. Here, 1 phases, you cannot work. So how do I work? On this proportion A and this proportion B, I put the composition. Those 2 proportions belong to the tie line, which means if I prepare this composition A, 83% water, 2% chloroform, and 15% methanol, I will have 1 phases only, just 1. If I prepare B, which is 1% water, you see a very small amount of water, 95% of chloroform is this reading, and 4% of methanol, I prepare B, I will have also 1 phases. So I cannot work in CCC with those 2. Yes, you can work with those 2 because A and B are not miscible. And if you have prepared A, prepared B in 2 different pots, you can mix them. They will not change in composition. They will stay. So let's go 1 slide below. So that's the same A, that's the same B that we got previous slide. Say now, and that's what you find in the literature, that's what Gilda just put on table. To separate this, you need methanol, this amount, chloroform, this amount, water, this amount. If you put the amount indicated, you get 2 phases. So let's say X. X is 80%, would be published as 8515. Okay. Then you find another article that say, oh, to separate this, you need to work with 1085 in water, chloroform, methanol. That's a lot of chloroform. That's very apolar. This one is a lot of water. It's very polar. No, not really. X and Y are exactly, from a CCC point of view, the same thing. That's why it's important to know what ternary phase diagrams are. This is not more polar than Y. X and Y are the same because X and Y belong to the same tie line. That's not possible. Come on, there is 80% water in one and only 10% water in the other one. It cannot be the same. They are not the same. They belong to the same tie line, which means they form 2 phases that have exactly the same composition. They have not the same volume. They have the same composition. So let's look X first. X, 80% water, I didn't put the ticks. I should, but you can on your you can add it on your paper. So water, 80% water. Okay, we have X on that line. We have 5% chloroform. Chloroform was there, I think. So that's 5% chloroform, and we have 15% methanol. 15% methanol X, belonging to that tie line. So X will produce two phases. One phase which is rich in water, which is A. We got composition here. And one phase which is rich in chloroform, that's B. And that's what we have in the tubes. But we have a lot of composition A and a very small amount of composition B. 96% of A, 4% of B. So what's the rule? The rule that's work only with equilateral phase diagram, distance A, XA times volume of A is equal to distance XB times volume of B. So if we have a large distance, we have a small volume to get, that's the lever rule, you know. If you can put the point here and you press strong here and you have equilibrium. That's exactly this. We have a large amount of A and a small amount of B because of lever rule. XA times volume equal XB times volume of B. Now if we look Y, point Y. Point Y, 10%, 85, 5, okay, to save time, you check that's correctly there. Same. We are on the same tie line. We have two phases, exactly A and B, because all phases you get in that phase diagram belong to the binodal line. That's why we need to know very well this binodal line. So that's A and B. How much? AY, which is very long, times the amount of A, must be very small, is equal to BY times the amount of B. Amount of B very large, 89% of B, 11% of A. So if the conclusion of the two articles is that's strange, we work with a liquid system with small amount of water, we get same result than when we work with a liquid system with a large amount of water. No surprise for a physical chemist. You are working on the same tie line, you are working in liquid phases with the same A and the same B. And that's true for any point belonging to that line. That's the very important point you have to realize looking at those phase diagram. That's why it's important. To change my CCC chromatogram, I must change tie line from tie line. So in that case, it means I must add this solvent, which is methanol, on same proportion of water and methanol, water and chloroform. I must add methanol to change tie line. Then I will change the proportion there and there. I will change more the water-rich side than the chloroform-rich side. Okay, on this. So that's the important point. So what we need in CCC, we need phase diagram. That's very easy to make. I'll tell two words. More difficult is to find the tie lines. That's a little bit more difficult. So how do we get a phase diagram? I'll just explain what we will do tomorrow in practice. For example, you have water, which an organic solvent. Do we ask if they have something we could do? I don't know if somebody has a phase diagram that cannot be found in literature and they would like to make it, because it's possible to make one in one afternoon. It's not very... You have one?
No.
If it's not published, you know, doing useful work, it's better than repeating known work. The good point of repeating known work, we are sure to succeed. Okay, so we have water, organic solvent, not soluble, and we are adding a compatible solvent with 2, and that's a type 1. If it's type 2 or type 0, it's the same, we can do it the same. So how do we do? For example, in that case, we will prepare a water blending solvent, say 25%. 25% of methanol, for example, and 75% water. So that will be this point, one phase. And then you make a titration, adding this solvent you are working on, drop by drop and shaking. So first drop, soluble, second drop, soluble, third drop, soluble, drop by drop, until you see here on the orange point, you need 2 phases appearing. And when you make the titration, it looks like it becomes cloudy. You touch it, it dissolves eventually. One more drop, it's cloudy, and then you get 2 phases. So you note this proportion. Then you prepare, for example, on this rapid drawing, 50-50 of blending solvent and water, this point. And same, you add 1 drop, 2 drops, drop, 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 drop. At one time it becomes cloudy. 1 more drop to be sure, and you get this composition. Then you make 75% blending solvent and 25% water, and same. Then on this one, you must prepare maybe a large tube, because you add volume, volume, soluble, 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 soluble. So let's change another a big one. And at certain point, it becomes cloudy. So you get those 3 points. Then you can start on the other side, making blending solvent plus organic solvent. For example, I prepare 50-50 and adding water, going this way. And when you add water, at one point, it becomes cloudy. Then you have those 4 points. You find in literature this point because that's solubility of water in the organic solvent, and solubility of organic solvent in water to get this point. And you have a good idea of the binodal curve. So it's not very difficult. I have, in the French courses, we have students of in between graduate and undergraduates that knows enough chemistry to do it, and you do that, and they do it. That's not difficult. Tie line now, that's more difficult. Personally, it's for tie line, when I want to be sure, I just prepare the composition I want to work with, and with Jan Gerhard parallel with the quaternary system, we parallelly did the same thing at the same time. You just analyze. Since I am in the Laboratoire des Sciences Analytiques, we have gas chromatography, we have everything like you have here. So you just analyze, and then you have no problem. If you know the composition, you will spot the location of the point. If you cannot analyze, there is trick that allow you to find where the tie line is. So this is estimation, tie line estimation. You prepare your composition X, noting carefully, I make this volume, this volume, this volume, if this is a volume diagram, or this mass, this mass, this mass, if this is mass phase diagram. You note everything you put in. So you know where you are for sure. You are on this position X, and this position X split in 2. The green one here and the red one on the top. So you look. For example, in that case, to make it simple, I say, oh, this split approximately in the middle. So my tie line cannot be this, because I am not in the middle. X must be in the middle of the tie line. So you look with your ruler, where can I find a way to have X in the middle? because that's what I see. And that's approximately here. Of course, it could be a little bit more, a little bit less, but that gives you interesting estimate where your tie line is. So X is probably this composition and probably that one, not that size because X green would be too short and X red would be too long, and not that side because it's the opposite. X red would be too short and X green would be too long. So it's probably this one. That's a rough way to use the lever rule to find the tie line position. The best way is this one. I take this composition, use it, use a Carl Fisher determination of water content, and then I have the water content. And with gas chromatography, if it's ethyl acetate, for example, very easy to quantitate ethyl acetate by gas chromatography or heptane by gas chromatography. Okay, on those things. Now we make it even more difficult, going for solvent. How many solvents can we use maximum? No answer. As many as you want. The rule is you must have two phases. That's not difficult. You take random, you get your kits mixing, you probably get two phases, maybe three, so that's a problem. So we can go 4 solvents, we can go 5. I'll stop to 4. Don't worry, you see slide 11 from 12. So when we have 4 solvents, we can reduce to 3 parameters making percentage, but there is no way to go down to 2. We want to put any proportion of 4 solvents. So I put light on this HEMWAT system because it's very useful for natural products. So HEMWAT in English, it's, I saw you are calling it differently. It means hexane, ethyl acetate, methanol, water. Heptane, actually. I put heptane, it's not big difference. Heptane, ethyl acetate, methanol, water. Why heptane? Because heptane, for those that are in the medical side, heptane is odd number 7. Hexane is 6 even. And it's known that 6, 8, 10, 12, you have strong interference with the living organism. 7, 9, little interference, which means heptane is much less toxic than hexane. It's much more expensive, so I understand if you use hexane, but it doesn't make big difference. It's very, very similar. So heptane, water, methanol, and ethyl acetate. It must be shown in 4-dimensional. So what I did, I prepared a Walter Conway style slide, because there is no other way. This is it. So let's see, water, methanol, heptane, water, methanol, heptane. Damn, I will not be able to put it like I put it on the slide. Methanol, water, heptane, ethyl acetate. When you look at this in 3D, you have different phases, and all are one ternary diagram. So for example, this is heptane, water, methanol, and you have a regular type 1 diagram with tie lines. You may not see, I'm sorry, you can look close when you leave. On that side you can see, that's better. This is water, ethyl acetate, methanol. That's a type 1 composition that we could do tomorrow. 2 phases, single phases. And this slide, that's the stupid side. Ethyl acetate, heptane, completely soluble, and methanol. Methanol, there is a little, it's not completely stupid. Here, you cannot see, but there is a little part which makes 2 phases. If not, it's single phase. And we have seen that one. And that one is heptane, ethyl acetate, water. Also, this one is very interesting. It works everywhere. You don't see any line on any binodal curves because it's two phases everywhere. Heptane and water are not soluble, or so small amount that I cannot show it on such big things. And ethyl acetate and water are not soluble also, and heptane and ethyl acetate are completely soluble. So here we have just tie lines, and the tie lines goes from pure water to the mixture of ethyl acetate and heptane you have selected. Okay, and now I combine those compounds, 4 compounds, and you can open it, and you have the HEMWAT liquid system. In this liquid system, we are defined a particular composition which is called Arizona. This is so let me see. This particular composition starts at, you can read, it starts at ethyl acetate water. So in the middle of water, and ethyl acetate is there. Okay. I should find. Okay, here. In the middle of water, ethyl acetate. And it goes to heptane, methanol. So heptane is there and methanol is there, and I will put this. That's why it's up. I cannot. Inside this line, that's the Arizona liquid system. Only this. So you see, it goes from heptane methanol 50-50 to water ethyl acetate, going through the whole diagram. So the rule is, like you have on the slide, A. Why it's called Arizona system? Because there is the guy that designed this. Its name is Margraf, Rodolphe Margraf. He is split in 26. Why 26? Because there is exactly 26 letters. The first one was called A, the last one was called Z. You want one in between, no problem. As long as you respect this rule, it belongs to that line and it works. So you start with A. A is no heptane, 1 in ethyl acetate, no methanol, and 1 in water. So that's this point. Water, ethyl acetate, 6. And the last one, Z, it's the opposite. It's 1 heptane, 0 ethyl acetate, 1 methanol, 0 water. And in between, you always must keep those two equal to those two to stay on the line. If you don't keep those two, and those, I mean ethyl acetate, heptane ethyl acetate, same number as water, methanol water, you are not on the line. You are, it works. I don't say it doesn't work. I say you are not on the line. Who cares about your line? Why are you so? It's very interesting to be on that line because we have continuous change on partition coefficient, only on that line. I mean, if you find partition coefficient on one point B, C, D on this series of proportion of solvent, then the log of this partition coefficient change with the amount of water you have in the system. So you can predict. That's very interesting. You can predict for all. If you have one, you can predict the other. So that's why it's interesting to move on that line. That's it. If you are interested in one compound only, you don't have to care about that line. You can use any composition of heptane, ethyl acetate, methanol, water, and choosing the best that's working best for you. But if you are interested to predict what will happen, you can say, okay, this C was okay, I'll try D. Or C was completely off, I'll try P or R. on the other side. And of course, A, which is ethyl acetate water, is very polar. This is 100% water, ethyl acetate, that's a polar system. And the last one, Z, heptane and methanol, that's the one we used yesterday, it's very apolar. So it means on the line, going from one side to the other, you have a wide differing polarities range. That's why it's interesting to get different separation of your mixture. And that was slide 12 out of 12. Thank you for your attention.